Hello everyone and welcome back to Math 127 Pre-Calculus 2. Today we will continue our study of analytic trigonometry with section 5.3, which is the double angle, power reducing, and half angle formulas. So in the previous lesson, we learned how to use sum and difference formula to evaluate trigonometric expressions involving angles that were not directly available from the special right triangle or the unit circle. Those formulas allowed us to create exact values using combinations of known angles. So for today, we will build on those ideas and introduce three new families of formulas that are derived from the sum and difference formulas. So as you work through this lesson, you'll notice that these formula are all connected. In fact, many of them came from or come directly from the identities we've learned in the previous section. So one thing I encourage you to focus on today is um, understanding where the formulas come from rather than simply memorizing them. So, the more connections you can make among those formulas, the easier they become to remember and apply. So, by the end of the lesson, you should be able to use the double angle formulas, power reducing formulas, and half angle formulas to evaluate expressions. And then verify, of course, identities and find exact trigonometric values. Okay, so again, let's go ahead and begin with the double angle formula. All right, so starting with the double angle formulas, the name itself tells us what these formulas do. The double angle formula allows us to evaluate a trigonometric function whose angle is twice another angle. For example, instead of working just the angle theta, we can work in with 2 times the angle theta or 2 theta. So you may notice that the formulas involve only the angle theta on the right hand side but produced information about 2 theta on the right hand side, okay, on the left hand side. So this is extremely useful because it allows us to determine trigonometric values for larger angles using information about smaller angles. So as we work through this example, pay attention to how information about one angle can help us determine values for its double angle. Also, notice that the cosine double angle formula can be written in several forms, as you can see here. Okay, understanding why those forms are equivalent is often more valuable than memorizing them. Okay, let's go ahead and work through examples um, applying the double angle. Okay, all right. So, for example, if you are given here the f sine angle theta is equal to 4 over 5, and then angle theta lies in quadrant 2, find the exact value of sine double angle of sine 2 theta, cosine 2 theta, and tangent 2 theta. Okay, before we are going to start, what we're going to do is to look at the given here. And so we do have sine theta, which is 4 over 5. And we know that if we are going to define sine double angle here of sine theta, sine 2 theta is 2 sine theta cosine theta. And we know that if we are to evaluate cosine theta, we need to have value for x and r. In this case, I know that sine theta is already there. It's already given here. However, we do not have given for the cosine theta. And to work on the value of cosine theta, we need to have value for x. With this, we will be using this given value, which is sine theta is equal to 4 over 5. Let me just go ahead and use this space before we get into this trigonometric angles with a double angle. Okay, all right. So we know that. So for the sine theta, okay, let me just go. Okay, for the sine theta, we know that sine theta is equal to y over r. Okay, and since we do have given here for the sine theta, which is 4 over 5, so we know that this is 4 over 5. So therefore, y here is equal to, that y here, oops, okay, so y here is equal to 4, and then r is equal to 5. Remember that this given angle is in quadrant 2. Okay, so it's in quadrant 2, meaning to say that the sign here would be x is negative, y is positive. Okay, so now since we do have value for y and r, let's go ahead and find the value for x. Given we have here r squared, the formula r squared is equal to x squared plus y squared. Okay, we know that r squared is 5, so r squared, and then x squared plus 4 squared. Okay, by doing the math here, so we will have 25 equals x squared plus 16. Subtract both sides by 16, we have 9. And then now we go get the square root on both sides. Okay, so square root on both sides, that would be plus and minus sign. And so we now have here plus or minus 3 is equal to x. Now we'll decide whether x is positive or negative. And earlier we have mentioned that this angle is in quadrant 2. So therefore x here must be positive. So therefore we will be accepting the value for x. That would be, sorry, the x here is negative. So we will be accepting the value of x, which is a negative 3 instead of the positive. Okay, so now we do have now all the values that we need, the x, the y, and the value for r. So now we can now go ahead and begin evaluating the given expressions here and then finding the exact value. Okay, so starting with sine 2 theta, and by looking at this double angle formulas, we see that sine 2 theta is 2 sine theta plus, times cosine theta. So let me just go ahead and write that. So this is sine, let me move this. Okay. Okay, so let me just go ahead and write all those values, that y is equal to 4 and then r is equal to 5. Remember that is in quadrant 2. Okay, all right, so we have sine double angle is equal to 2 sine theta cosine theta. Okay, so now we have 2 sine theta. We know that by definition of sine theta is y over r. So I'm going to go ahead and write that. Well, we'll have this the given there. Okay, 4 over 5. And then cosine theta, by definition, it's x over r. So x is negative 3 over r, which is 5. So we have negative 3 over 5. So now we now go multiply everything here. So we have the 2 times 4 times the negative 3, we get a negative 24 over 5 times 5, we get 25. Okay, so I believe this is already in simplest form, so this would now be our final answer. Okay, now moving on with the cosine 2 theta. Okay, so for, like I've said, cosine 2 theta here has many um, formulas. Okay, so you can use either of these three statements here. So in my case, let me just pick the first one here. You can use this one. It's okay. We already have value for cosine anyway. And then this one as well. You can use that. Okay, let me use the first formula for the cosine 2 theta, which is the cosine squared minus sine squared. Anyway, whichever formula you will be using, you'll get the same result. So if you're using cosine 2 theta is equal to cosine squared theta minus sine squared theta, which is now equal to, cosine is equal to negative 3 over 5 squared minus sine is 4 over 5 squared. So now we'll square both terms here. So we have 9 over 25 minus 16 over 25. Okay, subtracting this, so we have a negative 7 over 25. So this is now cosine double angle. All right, next up with the tangent to theta. Okay, so for the tangent to theta, we only have one formula for that, which is the last statement here, which is 2 tangent theta and then over 1 minus tangent squared theta. Okay, so I'm just going to go ahead and copy that and substitute the value. Okay, so we have it here, tangent to theta, which is equal to 2 tangent theta over, we have 1 minus tangent squared theta. Okay, again, by definition of tangent theta is y over x. So 2 times, okay, so definition of tangent theta is y over x. So that's going to be 4 over negative 3 over 1 minus, again, definition of tangent theta is y over x, so that's going to be 4 over negative 3, and then squared. And then we'll just simplify this. So that's going to be, we have there 8 over negative 3 all over 1 minus 16 over 9. Okay, so let me just go ahead and multiply everything by 9. Okay, so I can get rid of those denominator. Okay, so we have here, in this case, 8 over negative 3 times 9. So that's going to be negative 8 times 3. So that's going to be negative 24. Over, so we have here 9 minus 16. Okay, so that's going to be now negative 24 over negative 7, which is again positive 24 over 7. Okay, so there you go. So that's going to be our tangent to theta. Well, this is the final answer there. Okay, there you go. Okay, moving on to page 2. All right, so next one, let's have page 2, which is finding the exact value given the formula here. So in this case, what we're going to do is to identify what formula can we apply here given this expression. For example, if you have cosine squared 105 degrees minus sine squared 105 degree, let's just say 105 degree is the angle theta. So we see, okay, let me see. So let's say we know that, okay, from the formula. So let's say these are angle theta. Okay, so we have here cosine squared theta minus sine squared theta. If you're gonna go back with the formula of the double angle, we see a cosine squared theta minus sine squared theta, which is equal to cosine double angle. Okay, let me just show you so you know where I'm getting it. Okay, so as you can see here from the second statement, cosine double angle is equal to cosine squared theta minus sine squared theta. This is just what I applied. So going back now, okay, so now I can now say that this is cosine 2 times the angle theta. What is the angle theta here? We see that this is 105 degrees. So this is 105 degrees. So in this case, we have cosine 210 degrees. And then from here, we are now going to evaluate this applying what we have learned from the reference angle, right? So if we are going to visualize this, this is in quadrant, this is the, let me, okay, so we have here that the angle initial, okay, 210 degrees would be in quadrant 3, okay, 210 degrees. And we know that the reference angle here would be equal to 210 degrees minus 180 degrees. So that gives us a 30 degree, okay. So there will be a 30-degree angle here, okay. So remember, opposite of 30 degree would be 1, okay. And then adjacent here would be the radical 3. Okay, if you are going back with special right triangle. Okay, opposite of 30 degrees 1, and then therefore the adjacent of 30 degrees is radical 3. So if we are to once again evaluate cosine 210 degrees. So this is going to be a negative sign because it's in quadrant 3 for the cosine. And then since we have here x here is negative radical 3, so that's going to be negative radical 3 over the, let's say the hypotenuse here is 2. Okay. All right, so there you go. So that would now be our cosine double angle. Okay, 2 theta. This is double angle, okay, that cosine squared. Okay, so now moving on to the next statement. 2 sine 67.5 degrees, cosine 67.5 degrees. Again, treat these two equal angles as simply angle theta. Okay, so in that case, we have 2 sine theta cosine theta. And then you'll go back with the formula under the double angle. You will see that this given 2 sine theta cosine theta is equivalent to sine double angle, which is 2 theta. Okay, so in this case, I will now be applying what I have applied in here. So now we will get sine 2 times 67.5 degrees. Okay, so now we have here sine 135 degrees. Okay, so now evaluating this, I will be doing exactly what I did here. We know that 135 degrees, that would be in, okay, initial, okay, that would be in quadrant 2. That is 135 degrees. And then if you are gonna go get the reference angle there, that we know that the reference angle here, that would be 180 degrees minus 135 degrees. So that's gonna be equal to 45 degrees. So therefore, we are creating a 45 by 45 degree, and we know that this would be a radical 2, a negative radical 2. That horizontal line is a negative sign because it's in quadrant 2, and then this is 2. And by definition of sine, this is opposite over the hypotenuse, okay? So we see here, opposite side is radical 2, and then hypotenuse is 2. So we have radical 2 over 2, okay? Positive, because the y value here is positive since it is in quadrant 2. Okay, so therefore, this is now 2, um, the 2 sine theta cosine theta. Okay, let me just go ahead and write this. Oops, hold on. Okay, I just got confused with this part. I thought I would write 2 double angle there. Yeah, it's correct. This is cosine squared theta. Okay, please correct that. Okay, now moving on to the next two items here. If you are getting comfortable now, you can go ahead and pause this video and then try it on yourself independently. And then after that, resume the video and then compare your answer. Okay, so as you can see here, we do have exactly this similar process here from the last two examples. Okay, so going to cosine squared 135 degrees minus sine squared 135 degrees. Once again, we know that this is similar with cosine squared theta minus sine squared theta, which is equal to the cosine double angle or cosine 2 theta. So with this, we will now have cosine 2 theta, so we have here 2 times the 135 degrees. So that's going to be cosine 270 degrees, okay? So now let's evaluate that by drawing the 270 degrees. And we know that 270 degrees is located in the y-axis on the negative side. Okay, let's just say I'm going to go use a 0, -1. Okay, so by definition, we know that the definition of 200, I mean cosine, is the x value, okay, for from the unit circle. So in this case, we now say that cosine 270 degrees is equal to 0. Okay, all right, since we're talking about cosine, so the x value. Okay, so next one we have here the 2 cosine squared, um, 3 pi over 8 minus 1. Okay, so once again, going back with the formula. Okay, so this is like 2 cosine squared theta minus 1. Let me write that. So it's like saying 2 cosine squared theta minus 1. Okay, so if you are going to go look at the formula, this is the same thing as cosine 2 theta. Okay, all right, so now we can now say that this is cosine 2 times 3 pi over 8. So now we have here cosine. We have multiplying 2, so 8 will become 4, so this is going to be 3 pi over 4. Okay, now going back to evaluation, so if I'm going to draw that on the x and y plane, so again, initial side. Okay, so now we have 3 pi over 4, so we have 1, 2, 3. So it's in quadrant 2, which is 3 pi over 4. Okay, and then we know that the reference angle here, okay, so all we need to do is to subtract that from 180 degrees, which is equivalent to pi. And since the denominator is 4, so I'm gonna write 4 pi over 4. Okay, just to make it the same denominator with 3 pi over 4. So this is now pi over 4. Again, pi over 4 is the same thing as pi. So this is pi over 4. So now we can see that we are creating special right triangle, which is the pi over 4 by pi over 4, which is the y here now is radical 2. The x here is negative radical to y negative because it's in quadrant 2. Okay, so now evaluating for the cosine, this is now equal to that negative radical 2 over the hypotenuse. We keep on using the hypotenuse 2 whenever we are applying the special right triangle. Um, we base that from the previous lecture that we have. So this is now a negative radical 2 over 2. Okay. All right. Now moving on to the last statement here, which is letter E. Okay, so once again, treat this angle right here as angle theta. If you're going to look at the formulas, once again, there is a formula that is 2 sine theta over 1 minus tangent squared theta, which is the only formula we have for the double angle for the tangent. So this is tangent to theta. So therefore, this is tangent to, okay, 11 pi over 12. Okay, so simplifying this, we get tangent, we get 11 pi over 6. Again, I just multiplied 2 times 11 pi over 12. Okay, so now we'll go ahead and um, apply the formula, so sorry, we will be applying the evaluating of the tangent function here, okay? So we know that the tangent by definition is y over x. But let me go ahead and draw the coordinate plane here. Okay, so it's 11 pi over 6, so that's gonna be like 30 degrees. Okay. But multiples of 30 degrees or multiple of 11 pi over 6. Okay, so initial side here. So we have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so it's over here. So this is 11 pi over 6, okay, which is in quadrant 4, okay. So what we are going to look at here would be the reference angle, okay. To find the reference angle there, we will be subtracting the 1 revolution, which is the 12 pi over 6. I'm using 12 pi over 6 so that it would be same denominator with 11 pi over 6, because anyway 12 pi over 6 is just the same thing as 2 pi, which is 1 revolution. Okay, so in this case we have here pi over 6. Okay, so we have a triangle here which is 11 pi over, so not 11 pi of course, but pi over 6. Okay, so let me just extend that, and that's okay, right, for a triangle here. So this one is pi over 3. And we know that the opposite of pi over 6, if you will recall with our special right triangle, is equal to 1 if our hypotenuse here is 2. And then therefore, the x here would be radical 3. So therefore, since we are in quadrant 4. So this negative 1, which is the y, which represent the y value, is negative. Okay, so now we'll now go back with the evaluation of tangent 11 pi over 6 using its reference angle pi over 6 in quadrant 4. So by definition, we have here y over x, correct? And then we know that the value for y here is negative 1 over x is radical 3, okay? And so we just need to, once again, simplify this by rationalizing the denominator, which is the radical 3. So therefore, we have a negative radical 3 over 3, okay? So there you go for the tangent double angle. Okay. All right. Now I'm just gonna go ahead with the next example, which is the usual one that we always do is the verifying identity. Okay. So I only have here one example, since across all those sections in chapter 5, each of them have verification of identity. So up to this point, you should be getting, comfortable, I would say comfortable in verifying identities. Okay, you know the steps. That first step is to um, choose between these two sides which one for you looks more complicated. Okay, formula, I mean expression, and then we will focus on that side and then make it identical to the other side. Okay, so for me, the more complicated side here would be the left side, because as you can see here, the left side has triple angle, which is sine 3 theta. Okay, and then I'll make it identical to the other side here. Okay, so let me go ahead and start that. All right, so in this case, we have sine 3 theta. So what I'm going to do is to expand the 3 theta here. So I'm going to have now sine theta plus 2 theta. Okay, so as you can see here, of course, by the way, I will no longer be writing the other side. Okay, just pretend that I keep on, to save time for me to write over and over again the 3 sine theta minus 4 sine cube theta. Okay, I'll just be writing the equal sign and then the question mark, and then again the side here is just simply this right side of the original equation. Okay, all right, so but of course, in formal writing, you need to write that out in the statement. Okay, so next one, since I do have here two angles right here, so now I am going to apply the, what they call this, the addition or the sum of sine function from the previous section, from section 5.2. Okay, so once again, from the sine or the sum of the sine function. Okay, let me write the formula first. Okay, so you know where I got it. So the formula that I'm going to apply is whenever that sine of alpha plus beta, which is equal to that sine alpha cosine um, beta, and then plus cosine alpha and then sine beta. Okay, so I will be using this concept in order for me to rewrite the sine theta plus 2 theta. So I'm gonna go ahead and treat this as like angle alpha, and then this will be my angle beta from this identity. Okay, all right, let me go ahead and rewrite this now. So sine theta cosine 2 theta, oops, 2 theta plus cosine theta, and then sine 2 theta which is equal to, okay, that side. Okay, next one, what I'm going to do is to now apply the double angle under the cosine. Okay, so I will now make this just a single angle. All right, since our goal here is to have just those single angle on that side. Okay, that's my goal. Get rid of those multiple angles, okay, from each of those trigonometric function. In this case, I still need to work on with cosine 2 theta and sine 2 theta. And so in this case, I will be applying their formula. Okay, so I will have now sine theta. I'm just going to go ahead and use we know that we have multiple formulas for cosine double angle. What I'm going to use here is I'm going to use the 1 minus 2 sine squared theta. Okay, so we have here 1 minus sine squared theta. Okay, again, I replace this cosine double angle into 1 minus 2 sine squared theta. Why did I use that? Because, again, I plan to have exponent 3. So I'm looking for another sign that would increase my exponent into 3. Okay, that's the reason why I picked the 1 minus sine squared theta. Okay, and then plus cosine theta. Again, I'm going to replace now the sine double angle. We only have one formula for that, which is 2 sine theta cosine theta equals, of course, oh, I'll write ellipsis there. Okay. All right, next one, I will now be distributing the sine theta here. So I have sine theta minus sine, look at that, cube theta, okay? And then plus, now I'm going to go multiply this. For this, we have now 2 sine theta cosine squared theta, okay? All right, so next one now, we now get to um, what else do we have here? Okay, so now we are going to rearrange the statement here. We do have sine theta minus 2 sine cube theta plus 2 sine theta cosine squared theta. Oh, okay, no. Okay, so what I see here, okay, since my goal here is just to have sine theta, I'm sorry, I changed my mind. Okay, so since my goal here is just to have a sine function, so this first term is good, second term is good, but the third term is not good because it does have a different trig function, which is the cosine theta. So I'm gonna go ahead and work on with the cosine squared theta. And going back with the formula for the Pythagorean theorem, okay, that sine squared theta plus cosine squared theta is equal to 1. I am going to use this Pythagorean identity in order for me to replace that cosine squared theta. Yeah, because if I'm going to subtract both sides by sine squared theta, sine squared theta. I am left with cosine squared theta on this side. In that case, I will now have here the 1 minus sine squared theta. Okay, so let me replace that cosine squared theta. Okay, so now we have sine theta minus sine cube theta plus 2 sine theta. Okay, again, replacing that cosine squared theta. You see here, I just subtracted both sides by sine squared theta. Yeah, so I am left with cosine squared theta. So cosine squared theta here is equal to 1 minus sine squared theta. Okay, so 1 minus sine squared theta. Okay, then after that, I will now be distributing that once again. So cosine theta minus sine cube theta plus 2 sine theta minus 2 sine cube theta. Okay. Now, what we see here, we can now combine those like terms. So we have here sine theta plus 2 sine theta. Oops. Hold on. Let me just go complete my statement here. Okay, so we have now 3 sine theta. Okay, because that is just simply 1 plus 2. Okay, next, negative 1 and then negative 2 here. So we're going to have a negative, oops, hold on, something missing here. Oh, okay. Oh, okay. I think, let me just correct that portion. I think I have missed this portion here in the formula of cosine double angle. It should be 1 minus 2 sine squared theta. Okay. All right. Okay, so there you go. So now we will have here a negative 4 sine cube theta. Okay. All right, so in this case, we now have here the 3 sine theta minus 4 sine squared theta. Okay, let me now complete my statement now. Okay, sine theta minus 4 sine cube theta. Okay, all right, now as you can see now, so end of proof. Okay, so as you can see now, they are equal. I'm sorry about that. I missed that portion that I did not write the coefficient of sine squared theta from the formula. I just said 1 minus sine squared theta, which is definitely wrong. Okay, so it must be 1 minus 2 sine squared theta according to the formula. In that case, this would be, again, negative 2, negative 2, negative 2. In that case, we have here negative 2 sine cube theta. And then minus 2 sine cube theta. That gives us a negative 4 sine cube theta. Okay, so since they are now identical, so this would now be our end of proof. Okay, all right. Now moving on to the power reducing formula. So, as we move on to the power reducing formula, at first glance, okay, at first glance, the name may sound a little bit unusual. Well, the purpose of this formula is exactly what the names once again suggest. They reduce powers, which are the exponent of the trigonometric functions. Okay, so for example, if we see a sine squared theta, okay, or cosine squared theta, this formula allows us to rewrite those expressions without the power greater than 1. As you can see here, okay, that exponent of cosine here is 1, okay, so for all of the statement. So you might be wondering why we would want to do that, okay, as we move further into trigonometry or even in calculus or even in higher mathematics. Okay, expressions involving powers of trigonometric functions become very common. All right, so power reducing formula often simplify this expression and make them easier to work with. So as we go through this example, okay, as we go through this example, pay attention on how a squared trigonometric function can be transformed into expression involving a double angle. That relationship is one of the most important ideas in this section. Okay, all right, so in this case we have a given sine raised to 4x. Okay, um, does not, what our goal here is to have this trigonometric function not greater than 1. Okay, that's our goal. To rewrite this expression, this sine to the fourth power of x. Okay, let me just rewrite that. That sine to the fourth of x should be, okay, should be written where the exponent should not be greater than 1. Okay, so what I'm going to do is like this. Okay, so first I'm going to factor this expression. I'm gonna make it as sine squared x times sine squared x. Okay, let me use a parentheses. Okay, all right, I factor this. Okay, the reason why I factor that, because we do have a formula, okay, for the sine squared x, that would make the exponent reduced by 1. Okay, which is this statement right here. Okay, all right. I am not going to use definitely the Pythagorean theorem, because if it is Pythagorean theorem, it will still be giving me a cosine squared that is, once again, an exponent or power higher than 1, which is not our goal. Okay, so now let me use that formula. So which is 1 minus 2 cosine x over 2. And then we have here 1 minus 2 cosine x over 2. Okay, all right, now I'm going to multiply these two fractions. So this is like 1 minus 2 cosine x times 1 minus 2 cosine x all over 2 times 2 is 4. Okay, and then this is like again, I will just be multiplying this, okay, by FOIL. So 1 times 1, 1 times 2 cosine x. And then after that, I'm going to go distribute the negative 2 cosine x to 1. And then from each of those, okay. So now I will have 1 minus 2 cosine x. And then we'll have the next one. Okay, 2 cosine x. Okay, did you see that? 1 times 1 will have 1. 1 times negative 2 cosine x is this. Now, second term, negative 2 cosine x times 1 is negative 2 cosine x. Negative 2 cosine x times negative 2 cosine x is positive 4 cosine squared x all over 4. Okay. So now I will have to combine the like terms, which is the 2 cosine x, 1 minus 4 cosine x, plus 4 cosine squared x over all over 4. Okay, now what I'm going to do is I am going to distribute this 4 to each of this term. Okay, just to make it looking simple. So we have here 1/4 minus just cosine x, okay, plus cosine squared x, okay. Did you see that? So this is 1 over 4, this is 1/4, this is negative 4 over 4, this is negative 1, and then we have here 4 over 4, this is positive 1, of course, cosine squared x. Again, we still cannot say that this is our final answer, because again, our goal is to have those trigonometric function exponent which is just simply 1. Okay, the problem here is this, okay, that cosine squared x. Okay, but what we want to do here is to make it, again, we will use again the formula of the power reducing, and then I am going to use this statement right here. Okay, all right. So equals 1/4 minus cosine x, and then we'll have there plus 1 plus 2 plus cosine double angle over 2. Okay, so again, I just changed the cosine squared x using the power reducing formula, okay, which is equivalent to 1 plus 2x 1 plus cosine 2x over 2, okay. I will just be distributing the 2 here, so it will be uniform to the other terms here. So now we have 1/4 minus cosine x plus 1/2 plus cosine double angle, okay. I will just be adding the 1/2 and then the 1/2, the 1/4 and then the 1/2. Okay, so let me add those two. So this is now 1/4 plus 1/2 is 3 over 4. Okay, now I'll continue rewriting this cosine x. I'll keep those remaining terms and cosine double angle. Okay, so we have achieved our goal, having those trigonometric function wherein the exponent is only 1 or not greater than 1. If you are asking, can we combine this cosine x and negative cosine x and cosine double angle here? No, because the angle are not the same. Okay, so we cannot combine those two trigonometric function. All right. Okay, now moving on to the next item here. All right, now our final goal here is to go over with the half angle formulas. Now, notice how these formulas relate to double angle formulas we just studied. Okay, so earlier we started with an angle found information about twice that angle. Now we're going to reverse the process. Okay, so given the information about an angle, we'll determine the information about the half of that angle. So half angle formulas are particularly useful when evaluating exact trigonometric values that do not appear directly on the special right triangles like the 30 degrees, 60 degrees, um, 45 degrees, okay, or from the unit circle. So again, for example, if you do have that 15 degree, actually I do have that example here. For example, if you have 15 degrees or even this 105 degrees or let's say 22.5 degrees, um, often become much easier if we are to evaluate this using the half angle formula because it will give us those common angles that you can see in the special right triangles or the unit circle. Okay, so one thing to pay special attention that to is the plus or minus sign that appears from this formula. Okay, the sign depends on the quadrant in which the angle lies. Okay, so this is another reason why understanding the coordinate plane and reference angles remains so important, as you can see here, even from the previous example. So as we work through the example once again, make sure you determine the correct quadrant before selecting the sign of the answer. Okay, all right, let's go ahead and begin. Start with the cosine, 105 degrees. Okay, so let's go ahead and rewrite 105 degrees, okay, in a way that we will have an angle that when you get the angle that has a special sorry, angle in the special right triangle, or what we call the common angles. Okay, so what I see here, that 105 degrees, okay, that cosine 105 degrees, I can rewrite that in a way that I will have 210 degrees divided by 10, divided by 2. Okay, um, you remember 210 degrees. If you are going to get the reference angle of 210 degrees, you will get a common angle that we know. Okay, I will show you. Okay, so we'll have here equal to, we see here cosine. I'm gonna go ahead and use this formula. But the question here is that what is the sign? Okay, since 105 degrees is located in quadrant 2, where cosine is x. Okay, where cosine is an x value. So therefore, we are going to pick the negative sign over the positive sign. Okay, so we will now be having a negative. Okay, I have explained why is it negative, because 105 degrees is at quadrant 2 plus cosine. In this case, angle alpha. You see here, angle alpha, okay, would be the angle there. So therefore, I will be using the 210 degrees instead. Okay, so now we'll have 210 degrees over, we have 2. I'll just check the formula. Yes, okay, it is correct. All right, so next one, let's go ahead and simplify this. So we have 1 and then radical 1 plus. Okay, I'll go back with the coordinate plane. Okay, 210 degrees would be here. Okay, which is again, we are going to look for the reference angle. We know that the reference angle would be 210 degrees minus 180 degrees, which is equal to 30 degrees. As you can see there, it's a common angle, 30 degrees. So there is a triangle here, a special right triangle wherein there is 30 degrees, okay? So we know adjacent with 30 degrees is radical 3, okay? And since this is in quadrant 2, so therefore this is a negative radical 3 if our, again, hypotenuse is 2, okay? So now evaluating 210 degrees, this would now be equal to adjacent negative radical 3 over hypotenuse 2 over 2, okay? And then I'll just be simplifying inside this radical, multiplying everything by 2, okay? So this is like multiplying everything inside by 2 over 2. So that's gonna be now 2 plus, sorry, that's not plus, that's becoming negative sign, okay, negative radical 3 over 4, okay? So with this, we now have here that radical 2 minus radical 3 over 2, okay? All right, so there you go. So this would now be our statement, which is the radical 2 minus radical 3 all over 2. All right, let's go ahead and move on with letter B, which is the tangent 15 degrees. Okay, so now in this case, we will have, okay, let me go ahead and rewrite tangent 15 degrees in a way that I will have that common um, angle. So I see here that tangent 15 degrees, I can use 30 degrees over 2, okay, which is again half angle under tangent. Um, I use 30 degrees because 30 degrees we all know it's a common angle under the special right triangle. So now I can now use this formula for tangent half angle, which is again the sine. Oops, let me just go ahead. I think we have more formulas out here. Yeah, so you can use either of this formula. Okay, so you do have there that positive or negative radical 1 minus cosine over 1 plus cosine. Okay, or you can use the other formulas here. It doesn't matter anyway. Okay, so in my case, let me just go ahead use the first one here. Okay. All right, now using the first one here, which is the plus or minus, we know that the 30 degrees is in quadrant 1, and we know that tangent in, sorry, not 30 degrees, but 15 degrees. We know that the 15 degrees is in quadrant 1, and then we know that in quadrant 1 for the tangent is positive. So, okay, so I'm going to go ahead and use the positive sign. So now I will get the square root of 1 minus cosine 30 degrees over 1 plus cosine 30 degrees. And going back with, again, the coordinate, okay, so we now have here initial, and we know that 30 degrees is just in quadrant 1. And if it is in quadrant 1, then definitely the reference angle is the same as the given angle. Okay, so we know that adjacent of 30 degrees, this is equal to radical 3, given if we are using a hypotenuse which is 2. Okay, so adjacent over the hypotenuse is again radical 3 over 2. So therefore this is square root of 1 minus radical 3 over 2 over 1 plus radical 3 over 2. Okay, this is radical. Okay, and then continuing. So I'm just going to go ahead and simplify the fraction inside. I am going to multiply by their LCD, which is 2. So I'm just going to go multiply 2 over 2 to each of those terms. So now we will have equal to square root of 2 plus, sorry, not plus but minus the radical 3 over 1 plus, oops, 2 plus the radical 3. Okay, next I'm gonna rationalize the denominator of the square root. Okay, so rationalizing this, that would mean I will multiply by the conjugate of 2 radical 3. Okay, so now I will multiply this 2 minus the radical 3 and then 2 minus the radical 3. Okay, so now we will be getting now, okay, 2 minus the radical 3 squared. Okay, anyway, they are exactly the same. And then below here would be 2 minus 3. So now we will have, okay, so now we will have, so we know that this, let me just write that first so you can see. 2 minus the radical 3 squared over the negative, um, sorry, this is 4. Okay, 2 times 2 is 4. So we'll have here 1, right? 4 minus 3, we'll have there 1. Again, I got that from 4 because I used the formula that 2, okay, let me write it down here, okay? The formula x squared minus y squared is equal to x minus y, x plus y. So I just use um, this formula right here from the special factoring in this two denominator. Okay, so as you can see here, they are two binomials with different sign. Okay, so using this, you just need to get square of the 2, which is 4. Square of the radical 3 is just simply 3. So 4 minus 3 is equal to 1. Okay, now we'll get the square root of both numerator denominator here. So square root of the numerator is simply getting rid of that exponent 2. So now we have 2 minus radical 3. And of course, the square root of 1 is simply 1. So that would just be it. Okay? All right. So there you go. This is my last example for this particular section. Okay? All right. So now moving on to the checkpoint part. If you notice, I only have one here because remember the previous three example, I have asked you to do it independently and then compare your answer with mine. Okay, so in this case, I will be now asking you once again to practice the formulas. So as you again work through this problem, you have to ask yourself which family of formulas is most is I would say most appropriate. Okay, can the expression be rewritten in using a double angle formula, or would it be a power reducing formula to simplify the expression, or is there a half angle relationship that can help? Okay, or even the previous formulas that we went through. Okay, and so remember that one of the goals of this section is not simply to memorize the formulas, but to recognize when and why each formula is useful. Okay, so you can go ahead and work this checkpoint independently before continuing with section 5.4. Okay, so once again, today we introduced three important families of trigonometric formulas, which are the double angle formulas, power reducing formulas, and half angle formulas. These formulas greatly expand our ability to evaluate exact values, simplify trigonometric expressions, and verify identities. So as you continue through chapter 5, you'll find that these formulas appear frequently and often work together with the identities and techniques we've already learned. So be sure to complete the checkpoint problem and review today's example before moving on to the next lesson. Thank you for watching, and I'll see you in section 5.4.